Alright guys, so yesterday we talked about standard deviation and specifically looking at measures of spread. So we've looked at shape, or different shapes of distributions. We've looked at different centers of distributions and when to use which center, which one is most appropriate. And so yesterday we talked about measures of spread. And the first measure of spread we talked about was range, but we kind of decided that based on these data sets, when you get down into these two here, L3 and L4, range isn't really useful. It doesn't tell us anything about what happens in the middle. All we know is this would have a range of 16. This would have a range of 16. It just tells us what's going on the low end and the high end. We have no idea what happens in the middle. So these two, obviously two different data sets. The range doesn't tell us what's going on in the middle. So we need another measure, and that's when we got to standard deviation. So standard deviation is a little bit more precise measure of spread. And we looked at two different versions of this. Population standard deviation, and this is sigma. And we kind of broke down, again, this is going to be your population size. So how many data points are in your population. Lowercase n is going to be the sample size, and we use S sub x to represent sample standard deviation. So this is the technical stuff. The nice thing for us is we don't really have to know how to calculate it necessarily. You should be somewhat familiar with the different components in it, and we talked about that yesterday. But generally, standard deviation is going to give us the average distance from the mean of all the data points, and it tells us about the consistency of the data. Smaller standard deviations mean more consistency in our data. So our data points are closer together, they're bunched together. Larger standard deviation tells us that our data points are more spread out and they are less consistent. Alright, so we've got this other measure of spread. The problem with this measure of spread is it's still an average, and based on our discussions before, we know that averages are thrown off by skew. So if there's any skew in the data, if it's not symmetric, or outliers. Outliers are going to throw this measure off as well. So while this is good for symmetric data, maybe I'll write this on here. It's good for symmetric data. If we don't have symmetric data, then it causes problems. All right, one more thing we want to look at is just how a histogram or a curve would look with different measures of spread or different standard deviations. All of these are bell curves. They're all normal curves. So you can see the blue curve here, and it tells over here that that's a narrow spread. So this would have a small standard deviation. Which means our data points are really consistent. They're really bunched together, and they happen to be bunched together around the mean. The next curve is a green curve, a little bit more spread out, and we would call that intermediate spread or intermediate standard deviation. A little bit more spread out. Data points aren't quite as bunched together. So we've got a kind of moderate consistency in something like that relative to the other curves. And then the red curve, the last one, much more spread out, much less bunched together around the middle, and so that would be a large standard deviation, indicating that we have less consistency among our data. Alright, so just to intro this to get into another measure of spread, we want to first take a look at what a percentile is. A percentile measure that indicates the value at which a given percentage of observations of a group of observations fall. It's a very technical way of saying a percentile is a measure of the amount of data you are better than, greater than, or equal to. So a couple examples. Student that scores in the 80th percentile on a test has scored as high or higher than 80% of test takers. As high or higher. Again, this is kind of like a greater than or equal to. So 80% of the people are as good, scored as good or worse than this particular student if he's in the 80th percentile. The gas mileage, another example, the gas mileage of a car is in the 40th percentile. That means this car's gas mileage is as good or better than 40% of the cars in its class, meaning like if you're measuring SUVs or compact or sedan or whatever it happens to be. So that's a percentile, as good or better. A quartile is another way that we chop data into kind of groups. So quartile, very similar definition up here, but really we should be thinking quarters. All right, we're going to chop this data into quarters. Student that scores in the first quartile of a test, first quartile is going to correspond with the 25th percentile. Meaning that this student has scored as good or better than 25% of test takers. All right, same example down here, but now we're looking at the third quartile. The third quartile corresponds to 75th percentile. And again, hopefully you get the idea now. You're as good or better than 75% of the data. All right, so let's just take a look. The 0th quartile, if we had one, would actually be the minimum value. It corresponds to Q sub 0 or the 0th quartile. We usually don't call it Q sub 0. We usually just refer to it as the minimum. Bump up to the next quartile and you're talking about the first quartile. So that's the 25th percentile, like we talked about above. The second quartile is the 50th percentile, and this should, if we talk about what the 50th percentile is, that means that you are as good or better than 50% of the data, which means that half the data is below you and half is above. Well, we know that that means that we have another name for that, and that is the median. So we usually don't refer to this as quartile 2. We usually just call this the median. All right, so the median is actually the second quartile. It corresponds to the 50th percentile. Next one is Q3, or the third quartile. That's the 75th percentile, like we talked about above. And the last one, the fourth quartile, kind of similar to up here. You are as good or better than 100% of the data. We usually don't call it that. We usually call it the max. All right, so these 5 measures, or technically, I guess, 5 quartiles, if you want to call it that. It seems kind of weird, but these 5 measures we call the 5-number summary. And we use those specifically in box plots. All right, so once you've found this 5-number summary, you can actually create or construct this box plot. Box and whisker plot, we call them. And here are your quartiles up here. The minimum, Q1, the median, Q3, and the maximum. Those are the 5 things that you need in order to create a box plot for this particular data. The next measure of spread, and this is the important part, is what we want to do is we want to hone in on the middle. So this is the middle 50%. So that's what the box indicates on a box plot, the middle 50% of the data. And generally when we're analyzing data, we want to talk about where is the middle of the data. Well, that's what the box represents, the middle of the data, and specifically the interquartile range, or you can call it IQR, measures the spread, or how spread out the middle 50% of the data is. So the interquartile range is your next measure of spread. And we talked about before how when we go back to standard deviation is thrown off because it's an average distance. It's thrown off by skew or outliers. Well, if we look at this particular measure of spread, IQR, we're chopping off the top portion and the bottom portion. So any kind of skew or outliers is going to be kind of mitigated. The effect is going to be mitigated on the IQR. So this is a better measure of spread, or the best measure of spread, or variation, if you want to use the technical term, in our data for skew or outliers. So what we want to do is, I'm just going to summarize real quick some of the stuff that we've talked about. When we use mean, or we use mean for symmetric data, anything that's symmetric, so uniform distributions, we use mean, and also normal distributions we use mean for a measure of center. Anything that's not symmetric, so skew, or if we have outliers, we don't want to use mean because it gets thrown off. That's when we're going to use the median. Alright, for our measures of spread, we know that if it's symmetric, we can take the average because the average is going to be thrown off. So that's when we use standard deviation. Maybe I should put both symbols here. Population mean or sample mean. This is population standard deviation. This is sample standard deviation. So if your data is symmetric, we're going to use standard deviation. If it's skewed or has outliers, that's when we're going to use IQR in order to indicate our spread. So here's an example. Construct a box plot and find the IQR for the number of bench press reps done by a sample of linebackers at the NFL Combine. We want to construct our box plot, and in order to do that, we need to find our 5-number summary. Alright, so we would just take this, we want to find the minimum, Q1, or the first quartile, the 25th percentile, the median, Q3, and the maximum. This is our 5-number summary, and this is how we're going to construct our box plot. So pull up your calculator, enter that data in, and do one variable statistics, and that will spit out all of these data values. So let me go ahead and do that for you real quick. Alright, so I've entered all the data into this calculator here. You should get these same results here. You can see that the mean is 20.4. If you scroll down, it actually gives you the 5-number summary. Here's my 5-number summary. 10, 17.75, 20, 23.25, and 33. So let's go ahead and record that. So here's my 5-number summary. Alright, when you're constructing a box plot, here's what I want to see. I do not want to see you just construct the box first. What I want to see you do is go ahead and construct your scale down at the bottom first. Your minimum value here is 10, so we can go ahead and start this at 10. It goes up to 33, so maybe we go up to 35. And then in between, maybe go up by jumps of 5. So let me go ahead and do that and keep it symmetric. So again, I want you guys to start with the scale. This is bench press reps. So we want to put that label on there. And we want our scale to be pretty symmetric and representative. The gaps in between should be representative so that our box plot isn't thrown off. From there, we just go ahead and plot these points here, these 5 values from the 5-number summary. There's my minimum. My Q1 is 17.75, so a little above halfway between these two. 20. 23.25 is going to be up here. And then 33 is way up here. So your box plot, here's my box. This is my middle 50% of my data. So half of my data is going to fall within these values right here. And then my whiskers will extend. So your box plot for this particular one should not be symmetric because this isn't a symmetric distribution. What this indicates, the next piece of this is the IQR. So we want to calculate the IQR. And we calculate the IQR. This is just how spread out our first quartile and our third quartile is. So the way that we calculate that is just Q3 minus Q1. So my IQR, or my measure of spread for this particular data set, is going to be 5.5. That's how spread out the middle 50% of my data is. Let's go ahead and box that in. So a couple things I want to look at up here just in interpreting this box plot. Number one, you can see that this piece right here is a lot less spread out than this piece right here, which means within from the 25th to the 50th percentile, those data points are much closer together. And it's indicated on my box plot. What this does not mean is that there are less data points in here. Remember, this is 25% of the data that falls within here. That's the definition of what my quartiles represent. So quartile 2 or quartile 1 and quartile 2 are median. There's still 25% of the data on the box plot. Because this is closer together, it indicates that those values are closer together. So this 25% of the data is much more tightly bunched together, or much more concentrated in this area, as opposed to something like this, where there's still 25% of the data. There's still the same amount of data points, but they're a little bit more spread out. And you compare those two to, say, this quartile, where there's still 25% of the data, but it's much more spread out. So on the higher end of this data set, we've got much more spread than we do in the middle. It's much more tightly bunched together in the middle, specifically between Q1 and Q2, than it is between like Q3 and the max. Same thing down here, not quite as spread out as between Q3 and the max, but more spread out in this quartile. There's still the same amount of data points in this quartile from the minimum to Q1, but it's more spread out. The data is more spread out. So that's how we can look at box plots and kind of interpret what's going on. We can talk about how spread out data points are from one quartile to the next, whether they're tightly bunched together like they are here, or they're really spread out like they are in this quartile here.